All right, now we get on to the second group of detailed discussions of the contents of the course. And the first, then we have these three units, which are actually a relatively new set of units. They're covering 51 use cases, 51 values of X from a survey we did over the end of 2013 in conjunction with the National Institutes of Standards and Technology, NIST, who set up a big data public working group. NIST is very important. It does everything in an open fashion. It is agnostic to particular approaches. So it wanted to find out as much general information as possible about use cases. So in the first of the units, we look at uh, basically the whole process to produce these 51 use cases. We have an introduction to the process, and then we describe the five subgroups, definitions, and taxonomies. You will be thrilled to know that actually that subgroup tells you what data science is, it tells you what big data is. Then we go on to the reference architecture. This is going to be what we put on our cloud. Security and privacy is critical in this field. So we have an important subgroup in that area. It actually has 9 use cases which we don't even go through. And then we have the technology roadmap subgroup, which is basically tracking the issues raised by the other subgroups to see where they're going and what needs to be done with standards and other support aspects. Then we come to the use case, the subgroup I was involved in, requirements and use cases, and I give an introduction to the work of that group. A key part of the work of that group was the identification of 51 sub big data use cases, and they're divided into 9 different use case areas: government, commercial, defense, healthcare and life science, deep learning and social networks, research ecosystem, astronomy and physics, environment, earth and polar science, energy. This discussion here, and there are, has a total of 51 use cases, and I introduced some concepts which are the so-called features. What type of computing they need, what type of algorithm they need, and I label the use cases with some of those features, and I also give a brief introduction to the features. Then in the final unit of this section, this is a section, it's 3 units, I actually go through these features in detail. I summarize the features in the use case, which because they classify use cases. Then we go through a particularly important distinction between the SQL or database use case classification, which is very important, and the NoSQL use case classification. And then we have a whole set of other classifications like machine learning, graph-based, MapReduce, and those are chopped up and divided between these 3 separate lessons here. These things are just lessons. And there were just too many to do it in one lesson. Now we have, after that, we have, we're going to need to plot things in the following discussions of X informatics for e-commerce, and so to do that plotting, we want to use the PlotViz software, and so we have a side MOOC on PlotViz, the motivation of the software, introduction to its use, and we describe 5 possible uses here: doing a cube, a structured data set, proteomics, how you actually have multiple data sets, you rotate them in a synchronized fashion when you want to retain the relative orientation of the graphs. And then we go through a larger proteomics example, but then the further features of PlotViz, we do tools and examples in the last 2 lessons. So this is a side MOOC. You might use that side MOOC in other places. Now we come on to the next value of X. We had X equals physics earlier, and then we had what you might call epsilon X, small discussions of use cases, basically 1 slide each for 51 use cases. Now we come back to a detailed use case example, which is the what I call e-commerce and lifestyle informatics, represented by Amazon, Netflix, and Pandora, and things like that, which are built around recommender systems. And we start off with a discussion of recommender systems, posing the problem, introducing them. We mentioned this well-known Kaggle site, which has lots of nifty competitions, particular one involving Netflix. We give examples of recommender systems, and then we actually have a set of slides I found on the internet from Netflix who claim that everything they do is a recommender system. In particular, they invent the concept of consumer data science as underlying their company. So Netflix is a pretty interesting company doing a lot of challenging things with data. They're a very good example of a company enabled by data. I mean, the fact that you're able to record the rankings of movies by lots of different users allows you to actually predict for other users what they should use. A rather remarkable concept that I don't think was at all obvious a few years ago, but now it's just taken for granted. We then summarize what we've learned about recommender systems and give further examples. We use the so-called we use then very more technology, the vector space formulation, the different types of collaborative filtering, user-based, item-based. There's also content-based recommender systems, which we will mention. And then we come to the technologies which are needed, k-nearest neighbors, and also some comments on high-dimensional spaces. But now we actually go through the technology section. This is going through the Python and Java versions of the k-nearest neighbor algorithm. We do its visualization, which will use plotviz. We test the algorithms to see how good they are. We go through k-means clustering, and we do that clustering, which we've already done for other examples for recommender systems. And then we show what happens when we extend the clustering to more clusters than may be useful. We discuss the concept of local optima and general aspects of it, and then we actually go into a little computer science digression into what is heuristics. Then we come, as they say, to a totally different thing, parallel computing. And these actually use some examples I derived a long time ago. I hate to say it, it was 30 years ago, about how to illustrate parallel computing with society, and in particular by constructing in parallel the different parts of, in this case, a wall, but it would be of any type of large construction project. So that tells you why parallel computing is a homely thing, which you know all about because you use it every day in society. Because society is basically an organization of parallel people working together to presumably achieve both individual goals and global goals. The global goal is the parallel computing aspect, because parallel computing is getting lots of things together to solve a single problem. Then we have 3 units on cloud technology. And we discussed this concept of E more or less anything. That means X is more or less anything. And that's the same thing, obviously, it's more or less anything informatics. And why something called cyber infrastructure by the National Science Foundation is relevant. We go back, we've already discussed cloud computing in the introduction to the class. We go now in more detail about what it is from several people and points of view. We go with Gartner, the motivation, we looked at some Gartner charts. We go through many more charts here and look at in depth of some of the Gartner predictions. And then we look at some simple examples of cloud computing like server consolidation and why clouds are good to consolidate and replace lots of small computing organizations by one giant computing organization. We then expand in more detail and look at these layers in cloud computing, network as a service, infrastructure as a service, platform as a service, and software as a service. We go into a little more detail on one of the most important, platform as a service. That's the part of the stack where you have common software, like common clustering software or common MapReduce software to solve many different problems with the same software. We talk about how data is stored in the cloud, and what the architecture of cloud is, who the key people in the field are. And we come back and look again at what applications run on clouds and what don't. Security, we already pointed out, is critical. Fault tolerance is an important issue. And also the fact that when you do parallel computing, you need to work together on the same problem, and therefore you have to actually synchronize. So we discussed synchronization constraints. And then we discussed big data processing from an application perspective.